it's really good having engineers working with scientists, because the engineer is always thinking about how am I going to take that and apply it to something, where a scientist might be just literally trying to actually further our understanding of the basic science, which, those two together is a really powerful combination. And that's how I think you really do make the next steps in innovations that lead to total changes, not just sort of the next incremental product.
From EE Tech Media, this is Moore's Lobby, where engineers gather to talk all about circuits. I'm Daniel Bogdanoff. When it comes to R&D, I think we spend a lot of time on development and don't always get to dig into the research side of things. As part of Industry Tech Days 2021, we had the pleasure of being joined live by an industry-leading researcher, and we're bringing that interview here to the lobby for you. Let's jump right over to that live session. For today's keynote, we are joined by Dr. Jeffrey Welser, IBM's Vice President of Exploratory Science and University Partnerships. IBM Research is one of the world's most prolific and well-established research institutions, and they're undeniably on the bleeding edge of tech. They announced the first functional 2-nanometer chip earlier this year. Their AI is poised to help design hardware. It also did pretty well on Jeopardy. And they are a leader in quantum computing. Research has pushed the electronics industry into its current state, but its value can be hard to quantify in the moment without the benefit of looking back and seeing what developments drove progress. That's the challenge today's guest faces every day. Dr. Jeffrey Welser has more than just an insider's view of where research is taking us. He has a direct hand in making it happen. Jeff, thank you so much for being here today. As we bring you onto the stream, can you share a bit of your engineering origin story?
Yeah, so thanks very much for having me. I'm happy to talk to you. So actually, I think I knew I wanted to be an engineer back in 7th grade. When all I wanted for Christmas was a TRS-80 computer at the time, which dates me a bit. But I have to say, I loved the whole thing. I loved trying to install memory into it, all the kind of hardware stuff you had to do back then. So then when I started college, I knew I wanted to do something engineering. I actually thought I might end up in the software side of the world, but rapidly found I really liked hardware, and in particular physics and material science. So ended up getting my PhD in semiconductor device physics materials, working on different types of transistors, et cetera, and knew I wanted to stay in the research side. I actually thought about maybe being a professor for a while, but decided I liked the idea of working in an industrial research lab. And started with IBM right out of school, because they had some of the best research going on at the time in semiconductor chips, which was perfect for me. And so I've been happy doing that and a lot of other things ever since.
I'm curious to hear, how did you know that industrial research was where you wanted to be versus university or public sector research?
Yeah, I make it sound like it was a really easy decision, but the reality was, part of the reason I went to IBM was I was able to still be an adjunct professor at Columbia University at the same time for a few years, because I really was on the fence. I loved working with the students in universities. I still, throughout my career, have continued to work with students and professors. But I just found I liked the idea of being in an industrial research lab where, although I was driving a lot of research and publications and conferences, some of my stuff was actually also going into our development teams, who then go out into products. It was a kind of a nice direct path for having that kind of impact. So I just thought it was a good balance.
That makes sense. Now, you have, going through your CV and hearing your background, pretty much anything like cool that IBM has done, you have been involved in. Like any headlines from IBM, it feels like you're there. How have you been able to, be involved in so many groundbreaking, cool projects, and how have you kept yourself centered and focused on what actually is the future of this technology?
Yeah, I've been very fortunate with my career path here. I've really enjoyed the time I've had. And I think one advantage of working at a place like IBM, where our research labs really do everything from like moving atoms around to make new materials, all the way up to building giant supercomputing systems and then all the software on top, is you have an opportunity to explore different spaces. So I think, after being at IBM for about 5 or 6 years, I realized I really wanted to not just always be in my own lab, but rather be able to go out and work on other projects. So, found opportunities to try and work in areas around maybe circuit design or systems design, and then little by little also into the software side of the world. And it's been good. I think a lot of it, I talk to people at IBM about, younger people who are starting their careers, making sure that you go into whatever you go into with the idea of, I'm going to have some technical impact on the things I can do here, but also realizing that as you go into different areas, and particularly if you move up into management, you can't solve all the problems, but you can be there to offer, a perspective and an ability to really think about it from a broader sense. And I think that's been a sort of the key to trying to find ways that I could contribute in areas that maybe weren't my PhD.
How do you balance your own perspective and experience with the expertise of people on your team? What sort of advice do you have for folks in that situation?
Yeah, I think I remember the first time I started to manage a software team. My first thought was, I'm going to go read all about this software stuff. I'm going to really learn it in depth. I'm going to try and really help them out with their project. And, after about 6 months, I realized that I was driving them and me nuts because I was never going to learn it at the depth they had. So I could never offer that kind of technical experience to them. But what I could offer was, insights into how what they were doing could help us, further some of the goals we had at a higher level for the systems we were building or some of the solutions we were trying to do for specific clients at the time. So really being able to offer that level of perspective, and then when they had problems, offer resources to try and go help them solve their problems with real experts, and not necessarily think I was going to solve it myself.
In your overall work, like I said, you've been involved in a lot of different things. How has that changed your perspective on like reading news headlines and seeing how technologies become conceptualized, mature, and then eventually get implemented in the real world?
Yeah, it's interesting because you read about some really exciting stuff in the news, including stuff coming from IBM or from universities I've worked with. And I think remembering that the excitement comes right at the moment of discovery in many cases, which is fantastic. That first time you get the transistor to work or you get the new technology to work. But oftentimes there's at least a 3 or 4 year path ahead of that before you're really going to see it get onto a product, right? So tempering the excitement of the initial discovery with the path of the hard work still left ahead to make it actually have impact, particularly in hardware. Software can be a much faster path, of course. So I think when I read stuff now, I tend to get excited about it and then immediately think, okay, so if they've done this, they're still going to have to do that before they're going to get to the product stage. But that's okay. I think that's actually also part of the fun.
I feel like that's a little bit like watching movies with someone who knows that field very well, as they they start to pick apart, like, oh, well, they wouldn't do it that way, or they would have to do all this other stuff before they actually, could do what they're doing. So it sounds like you maybe have that mindset going into reading the news as well.
Yeah, I do. At least in the newspapers, I definitely do it in the newspaper side. I will say I try not to be a killjoy at movies, though, even though my mind might be saying that physics would never happen.
I am also used to that elbow in the ribs of like, hey, stop ruining the movie for me. As we talk about the early stages in the whole life cycle of technology, can you speak to the importance of research and how that impacts the future of what technology will become?
Yeah, I'm really passionate about the research side of the world. I've spent time in development in other places in IBM, but I think research is my own passion, but it also really is key, I think, to keeping ahead in innovation. No matter whether you're talking for a company or a university or a country, I think that it's really been important the way the government has funded research at universities, industry funds research at universities, industry funds research internal to ourselves. And what it really does is lays a base of advancing the science and technology that raises all boats in many cases, right? So you're able to actually get that next step forward in a material or that next bit of physics demonstrated. And then there's going to be a whole bunch of people out there in different companies and different universities who figure out, hey, I can now take that and do this. And you never even know necessarily all the things you can do with that new material or that new structure you just created. You have the idea you were going for in many cases. And I think that's why it's really good having engineers working with scientists, because the engineer is always thinking about how am I going to take that and apply it to something, where a scientist might be just literally trying to actually further our understanding of the basic science, which, those two together is a really powerful combination. And that's why I think you really do make the next steps in innovations that lead to total changes, not just sort of the next incremental product.
This keynote is brought to you by OKDo. OKDo is a global technology company specializing in single-board computing, education, and IoT. They work with leading technology companies and offer customers the latest products, innovations, and design services wherever they are on their SBC and IoT journey, from students to entrepreneurs to professional designers to engineers and developers. And now back to our interview with Dr. Jeffrey Welser of IBM. So how do engineers and scientists work hand in hand? If me as an engineer, and if I'm designing hardware, working with silicon, or more exotic materials. How do I look for research and find scientists and organizations that correspond to what I'm working on and may impact my day job?
Yeah, I think it's important to work in areas where you've got a lot of multidisciplinary work going around you. In universities, that's sort of natural. It's not always as natural in companies because at IBM, we're very fortunate to have a really large research division, about 3,000 researchers. So we have a huge blend of scientists and engineers together. That's not always true. So in those cases, going out and making sure you're keeping track of literature and conferences where you get a mixture of the scientific inputs as well as the engineering inputs, I think is key to that. Interestingly, when I was I was running a program for a while funding nanoelectronics at universities, trying to find new phenomena that could be a different type of switch, a different type of transistor. Our very lofty goal was to replace the silicon transistor when Moore's law stopped scaling. So it was certainly not something we ever did, but it was a good sort of goal to think about. But the interesting part was we tried to pull together then physicists and material scientists and theoretical physicists as well as experimentalists, and of course electrical engineers and computer scientists to think about what would a new switch look like. And I remember the first couple of meetings we had across the teams, we spent time with the engineers just literally explaining to the scientists, what's a threshold voltage? Why do I care about a threshold voltage? What does it mean to have a digital switch? And of course, then the scientists were explaining things like, what the limitations are at room temperature, why you can't do certain physics at room temperature, and what it would mean to cool it down. So just those sorts of conversations to get the language right can be really complicated, but they were also some of the most fun conversations we had in that whole program.
Yes, there's a lot there, and I want to unpack. We touched on AI, device physics, quantum computing. So I want to get through that, but I want to hang on the research thing a little bit longer. As scientists are doing research, and as you see research progress at IBM, what percentage of it actually makes it into the hands of engineers, roughly, and what of it is just, oh, that's interesting, and we kind of shelve the idea for the future?
What we try to do is we have kind of a portfolio of projects. So we say that probably about 40% of our work is aimed towards things that we think can have impact on products in the next 1 to 2 years. And what we mean by that is really it'll get out of research and go to development. There still may be, a couple of years ahead of that before it actually gets into a product. And in that realm, we expect that, 80 to 90% of what we're doing should really go out there. It should be well enough honed that we know we're building the right pipeline in the development needs. The next tranche is maybe 30% that we think will be sort of more science work that we think could have impact in 3 to 5 years. And in that realm, we hope that maybe about half of it actually plays out to something that actually will go into a product. And then we have our exploratory work, which actually is the stuff under me for the most part. And that's the last 30%. And there we're looking very far out. So even if we're right on what we're doing, we figure at least 5 years before we'd be able to even think about having impact. And in those cases, sometimes that science doesn't even directly align with a specific product or idea. It's more, this is an area of science we know we need to develop and just advance as an industry. So let's work on it. And there, it's hard to say, maybe 20% actually has direct impact, but we hope the other 80% it's still advancing science in ways that has at least some sort of tangential impact to what's happening.
Is that frustrating to see maybe only 20% come to fruition, or is that just the nature of the beast?
It definitely depends on your mindset, right? I mean, the people who like to work in exploratory science, where they also get their satisfaction is, are we actually making advances that get into Nature and science publications? Are we out in conferences and leading workshops? Because hopefully, even though it may not be something that IBM puts directly into a product itself, it's advanced the scientific field in a way that we believe will help us, longer term. So I might not be able to draw a direct line to say that came into there, but hopefully I can say that whole area there built this whole field, which then created this, which then created that.
Understood. Research is always, in my experience, there's always the funding debate. There have been some, maybe a battle in Congress about whether government funding should go to semiconductor research in corporations versus national laboratories and universities. Can you speak to the value of both of those and your thoughts on how the government should be involved in research?
Yeah, well, first of all, I think that the key point for me is the whole idea of this public and private partnership is key to all of this, whether it's funding or the kind of research we're doing. So I'm really excited to see what's going on right now in the federal government for really increasing the funding in general. Whether it's the Endless Frontiers Act work or the CHIPS Act. I mean, getting money into semiconductors, getting money into basic science and engineering, I think is incredibly important. It's something we count on the government to be able to do that funding. Now, whether how much should go into a university versus a national lab versus even to companies, I think honestly that's going to be a debate will continue throughout, and it really depends on the nature of the work. A lot of the basic science work is going to be done in universities and national labs. That's great, and we count on that because we can then draw from that as industry. There may be areas though where we want to translate that more rapidly. I think that's always one of the challenges for industry and universities. Always is that sort of impedance mismatch. How do you best transfer quickly from a university a great idea into a commercial sector where it can have impact? So there may be opportunities there for some joint funding actually makes sense. And of course, we work directly with universities ourselves and fund them from our side too, because we always want to make sure that those connections are kept strong, because that's the best way to make sure innovation actually does make it out to the market.
On that note, when we talk about government and funding and all that, there are a ton of different awards out there. Some that the audience will know really well, like Nobel Prizes, and others are maybe a little less known to the public, but equally prestigious. Can you describe the feeling of having someone on your team or someone in IBM winning a Nobel Prize? It's happened 6 times.
Yeah, it's pretty amazing. In fact, I was fortunate that one of the people who won one was actually a former member of the Almaden Research Lab when I was the director out here in California. And he's a professor at Stanford at this point. And some of the work he'd done early on at IBM before he became a professor led into it. So we had him come down and speak. And just this idea that we went to his old lab, that he was sitting there working on some optics stuff way back when, and suddenly they came to a whole breakthrough in a way to actually image chemical molecules. It's so exciting. You feel kind of by extension, I know I had nothing to do with it, but at the same time, it just feels good to have that kind of smart guy around.
Are they kind of like untouchable in the office, or is it just like, hey, Joe won a Nobel Prize?
Well, I think actually within the community, they are still just other researchers. I mean, the thing is, at least everyone I've ever met who's won some of these major prizes, they won them because they're just really good at doing the work they do in their science, and that means a lot of collaboration. So you don't get there without having a team that you're leading, that's a very large team, and you're collaborating with a lot of other scientists, which means you always have that humbleness about, hey, I didn't get there by myself. And I find that they can still be some of the people that you can go to ask interesting questions, and they've got thoughts in areas that you wouldn't even guess.
Yeah, I could see that for sure. Definitely a team effort. So let's transition a little bit and talk about Moore's Law. It's one of those things that we all learned in Engineering 101. And every time it comes up, some people are like, yeah, Moore's Law. And other people just kind of get a little cranky. So, it's like, oh, we have to keep up with Moore's Law. Can you talk about how your work contributes to Moore's Law? Is Moore's Law going to go defunct? Is it still, a law, or is it more just kind of a theorem at this point?
Right. Well, I would say it's always been the reality of Moore's Law. It's always been a law that was created because we've all worked to make it happen, right? So it was basically just an observation, as everyone knows, by Gordon Moore early on in the 60s that, hey, we seem to be doubling the number of components on a chip every year or 2 years, depending on when you look at the law. And it then became sort of a mantra that, okay, it looks like we can do this, let's do it. But to actually make it happen, there's nothing about the law that happens automatically. It's all the things that are necessary in the equipment industry and in the manufacturing world and the designing world. Realize that we've got to work in sync. The reason we had sort of the ITRS roadmap for so long was if you're going to hit a node every couple of years, well, the materials guys need to know how thin the materials have to be, how thick, closely controlled do they have to be, what's the etch rate's got to be, what lithography do I need. So all these guys have to work together. And if you have a common target, then that helps. So that really drove it forward. Now, obviously, we also were helped by the physics of scaling at the time, Dennard scaling. So Bob Dennard's a researcher from IBM, but he was the one who figured out how you shrink the transistor in a manner to make it have more performance but constant power density. And that was key to Moore's Law working for at least 30 of the years it was going on. what I think caused a lot of people consternation now is that classical scaling really stopped somewhere in the mid 2000s because leakage currents and other things started to take over. So while we've continued in many ways the spirit of Moore's law to continue to have more and more components on it and the performance, the way we do it now is much more. I don't want to say ad hoc, but it's much where you got to grab this and that, and maybe we're going to do it by multiple cores, or maybe we're going to do it by trying 3D stacking or different types of interconnects. But this ability to continue the performance improvements every couple of years is really critical. I mean, regardless what you name the nodes, which is what everyone focuses on, it's are you really getting more performance for the unit area, the unit power, the unit dollar you're putting into it? And that, I think, has continued, and we need to continue it as an industry.
You mentioned power a couple times, and I know I've talked with our chip team quite a bit, and the joke is that every month of development adds a watt of power. Can you talk about thermal management and the importance of thermal management and power on ICs and what's being done to help reduce some of that?
Yeah, and that is really probably the key thing that's been the inhibitor to continued performance improvements. The easy way from Moore's law, where you were just scaling and shrinking, is just this power density that goes on. And I think that that's the reason, of course, that we don't really talk about the frequency of chips going up anymore, right? So one of the very first things we realized is you can't go up to like 5, 6, 10 gigahertz. You can, but the amount of power you're creating is just huge. So instead we go to multi-core or even sort of massive multi-core like a GPU, right? So finding ways of changing architecture where you can run things at a more reasonable speed and live with parallelism to get your throughput has been the key way we've managed power. And in today's chips, you can't even run all the transistors full out at the same time. You just melt the chips. So you figure out ways of powering things up and down and moving things here and there in terms of workload. So it's really increased the importance of the interaction between device designers, circuit designers, system level designers, and even the people who are running software and workloads to think about how that workload's going to run on it. So I think that is the best way to think about how we're going to manage power. Now, what you were talking about is how do we actually manage from a thermal perspective? Can we find better ways of cooling chips and finding better ways of actually managing it that way? And absolutely, we're continuing to try and make improvements that way. Obviously, systems used to all be water cooled way back when, and then we got rid of that. Well, water cooling is certainly still around in some of the bigger systems today because it makes sense to be more efficient. But the amount of energy it takes to actually do cooling has to be part of the system costs. And so, the idea of cooling our way out of the power problem, I think, sounds attractive until you actually think through how is it really going to work. I don't want my cell phone to be water cooled for sure, but even a big data center, it's not clear that it's a win always to do it. So finding the right balance of yes, we can do better cooling than we do, but can we always figure out ways to get the performance without producing excess heat power is really a better path when we can.
Yeah, I guess like my body is water cooled, but I still turn on my fan sometimes, right?
There you go. That's right.
Now, IBM has been a leader in chip technology for years, like inventing MOS DRAM in the 80s, UV photolithography, which is still used widely everywhere. We've recently been seeing talks of 2-nanometer transistors. Can you speak through is it just a spec? I know that in some architectures, like they say, it's a 10 nanometer device, but maybe that's what the mask is and not the actual device. Can you speak through some of the ins and outs of that 2-nanometer device that you've announced?
Yeah, so for all the architectures now, the node names have become somewhat disconnected from the actual feature sizes. Now, we talk about 2 nanometers, what we're really meaning is that the size that we've shrunk things down to in various dimensions will allow us to get the kinds of improvements we expect to see from a Moore's law progression, right? From going from 5 nanometers to 2 nanometers. And we actually have a working chip, and the transistors show they're functional, and all that kind of stuff. We still have several years before that becomes into manufacturing. But it really was important to say, yeah, you can continue. We do see proof that you can continue down to this next node in terms of density and performance from it. Now, the transistors to do these don't look anything like your grandfather's transistor, right? These things have multiple layers of silicon in them, and they have these nanowires and ribbons. But it's amazing what you can do to maintain the progression of the performance that you need to keep systems running, while still maintaining the power issues that we've talked about and all the control we need in terms of the tolerances and things to make it yieldable and manufacturable in the end.
How does IBM stay a leader in chip development, even though they're not a volume wafer manufacturer?
Yeah, well, we've done it really through all the partnerships we created. This really started back in the early 2000s, partnering with other companies who do have high volume needs for chips as well. So currently, of course, Samsung and now Intel even are forming partnerships with us. But we've been doing this with lots of companies since the early 2000s. And that what that allowed us to do was a couple things. First of all, obviously by pooling resources, you have a more resource to go into the work that goes on, but you're also pooling ideas from all these different groups too, and really thinking about what do we need in this next node of process to really make something that's useful for high performance chips. And we really focus a lot on the high performance logic chips, things that go into high performance computers, our own mainframes and high end servers on our side. But then our partners take that same process technology and they may go use it in other desktop systems or other servers or in consumer electronics, et cetera. We have partners in the tool space, the equipment space. We have partners who are more in the R&D space. We have partners who are actual IDMs or people who actually want to go make the chips themselves out there. And we've even had fabless partners in who've been actually wanting to make sure that the technology that we're producing will be used by fabs that they can then go and make chips in.
As we get down to 2 nanometers, we're awfully close to getting into the angstroms here. Are we going to see that in the future? Are we going to need new materials? What's that going to look like?
Yeah, I think there's no question that eventually you have to stop removing atoms, right? You get down to the last atom, you can't scale by removing it. So yeah, there is that. But as we were discussing, the dimensions we talk about now, they really are more like a node name, and there are certain things on the chip that certainly are 2 nanometers or even less than 2 nanometers. But at the same time, it's not the same as it used to be, where it's the pitch of the wires. But what you really hit on was exactly the case. It really is about constantly finding new materials and new structures. So the transistors today don't look anything like they used to. There's multiple nanoribbons of silicon in the systems. You used to do the FinFETs. You used to have just the 3D. You used to have the planar transistors. So finding new structures to control it and new materials to control the electrical fields at these really small dimensions is key. And we're going to see more and more of that. And I think the most interesting thing we're seeing is now, as we start to think about more specialized hardware. So we're always going to have sort of the path that says we want to continue, we call it Moore's Law for lack of a better term, but basically the high performance computing digital von Neumann systems. And we definitely want those to continue to increase in performance every couple of years. In parallel, more and more the industry is looking at, well, we have other workloads that might use more specialized hardware, AI being, of course, the one that's been the most obvious over the past, say, 10 years or so, but now increasing in quantum systems. So I think that's really a very new area of semiconductors, which I think is opening up whole new possibilities for the kind of devices and structures we make.
I want to get to quantum, but you mentioned AI, so I want to touch into that first. When I think of AI, I often think of training a neural network, doing TensorFlow, that sort of thing. How does hardware and AI, how do they get married together?
Yeah, so you're exactly right. When we talk about AI today, that's usually what we mean. We mean deep learning neural nets. That's the main workloads that really kind of had a breakthrough. And if you think about the history, those were known about back certainly in the 70s and 80s, but even back in the 50s. Carver Mead was talking about this at the time, but no one could actually get them to really do anything. And really the breakthrough came because of hardware. Well, it came because of two things. If you look around up until about, say, 2010, 2011, the accuracy of a neural net for, say, image recognition was, maybe 30, 40% error rates. So, even the largest neural nets were not doing very well compared to humans. Then suddenly there was this rapid decrease in error rates, like from 2012 down to 2015. It was just amazing, to the point where somewhere around 2015, 2016, the best trained neural nets actually had lower error rates than humans for image recognition, for example. And the two things that allowed that were not actually that the neural nets got better. The algorithms and things were the same as they always were. It was one that we had enough data now for training. So the internet has lots and lots of data that's digital, that can be labeled, so you can actually train the neural net. I always joke that the reason neural nets are good at finding cats on the internet is because there are a lot of cats on the internet, so you can have a lot of training to go do it. But the second thing was GPUs. Basically, someone realizing that the normal architectures we had were not very efficient at running these neural nets, and you need to run a massive neural net to do it. GPUs just happened to be really good at the same kind of math that you need in the neural net, right? They were obviously created for graphics processing units, but that math that you need is basically matrix applications is exactly what you need for neural nets. So once that we realized, suddenly we had this whole ability now to see the things we're seeing today.
Can you tell me a little bit about how IBM is involved in AI and maybe a little bit about AI hardware composer?
Yeah, sure. So one of the things we started a few years ago was the AI Hardware Center. So this is, again, all these things we do with our partnerships with our partners out there across the space. And it's really focused on how do we build even better chips and hardware for running AI systems, right? And I think this is something that GPUs work great, and we continue to use them, of course, ourselves. But we're seeing a lot of other companies as well make their own versions of chips to do both training and inferencing in AI. So we created the hardware center to do exactly that. And so we're looking at what are different architectures you could use to actually go after this. We also, though, are looking even further out. You were talking about materials earlier. So AI is a very different kind of workload. It's something where what you care about is the final answer, right? Is it a cat or is it a dog? You don't actually care about the math in between that much. So it's very possible you can use, say, reduced precision in that math. So, which sounds like complete, heresy. We always really go higher and higher precision floating point. But in this case, I don't care if the math is not quite right in the intro. If I'm using 8-bit math or even 4-bit math, as long as I get the right answer in the end, that's a win. And that's important because every time you have the number of bits, you actually save in power and area by 25%. So it's a huge win when you do this, right? So we've been focused on that. Are there ways to go to reduce precision? And the natural extension of this is the human brain, which is basically analog, right? Our brains are really good at recognizing cats and dogs, and our mom as she walks down the sidewalk. But they're bad at matrix multiplication. They're really bad at floating point. But so somehow they do this with these very rough analog components. So we are looking at that. So are there ways of making neurons or things that do the kind of work a neural net does that's an analog component, right? That's a different kind of material. Resistive memory, for example, is something that gets looked at. And we're having some really good results on how that actually could be done. And so finding, you can actually have these analog type neural nets. They end up with outputs from the actual answers that are almost as good as what you see in a digital system today. And I think that there's no question you can continue to go there. And yet they could be like 100x lower power. So, I mean, this is a huge win in terms of what it takes. Because unfortunately, GPUs are great and these neural nets are great, but they take huge amounts of power in large data centers in the cloud to actually do the training in particular. And even inferencing can be a fairly power intensive operation afterwards. So analog, we think, holds a really good hope for that. I realized I didn't get to your question, hardware composer. So one of the things we put out was something to let people start to play with configuring different types of hardware and running AI on it. Because one of the things we realized is it's one thing to say it's all neural nets, but all neural nets are not all neural nets. They're all different, right? There's different types of structures, and there's a lot of work actively in the community, on the theoretical side, the software side, to think what's the best neural net for doing, generative networks, for example, versus convolutional networks versus language processing. So thinking about how that affects the hardware you might want to have to be able to run it as efficiently as possible, and maybe combining analog and digital. That's something that we're playing with internally, but we realized, hey, we could put this out there for people to go use, and they can go play with it and come up with different ways of simulating and seeing it. And we can all learn together what might be really good ways of creating new hardware hybrids even that could be more efficient in the future.
It's almost Asimovian. Like in the early, iRobot books, he talked about robots with potentials, and that sounds very similar to analog cores. You mentioned that power was lower for analog cores. Are there any other benefits, and why would anyone go analog versus digital?
Well, power is certainly by far the biggest driving force. I think we're still learning what other advantages there might be. There are some hints that perhaps going to lower precision or analog can be a little more robust. One of the problems that we do have with neural nets is they can overlearn something, right? So you can learn something so well, but you're picking on some specific feature of the image, for example, you're trying to get at. So then you can be easily tricked by something else. The brain is much better at not doing that, and no one necessarily knows why. But one of the thinking is maybe if higher precision actually leads to more overlearning because you're able to get more precise than what the image actually is coming in. So there's hints at that, but I think this is all speculative at this point. Really, the driving force for most of us right now is get the power down. We have to get to the level that we can actually run much more efficiently.
Interesting. Yeah, I've heard of overtraining being an issue in machine learning training models where you essentially train your machine learning model just on your data set and that's all it recognizes and not
Yep,
the new information coming in.
exactly.
As we talk about cores and types of computing with GPUs and processors, we got to touch on quantum computing. Can you what is it, it seems like black magic and it's just all these like voodoo and spinning bits and qubits the right way. Can you, for people who aren't familiar, lay out what is quantum computing and why is it important?
Yeah, yeah. By the way, you're not alone in thinking it's black magic. There are people that the physicists have also been quoted saying, if you think quantum computing makes sense, then you actually don't understand quantum computing. So, anyway, the idea with quantum computing is we know that there are problems out there that are they're so big that there's no way the largest classical system you could ever build could ever do it. Mostly because it has to explore so many different options, so many different states out there, right? And it was actually Feynman back in the early 80s who was the first one, Richard Feynman, the physicist, who first one to say, quantum systems themselves can be in multiple states at once. It seems like you should be able to use that to somehow represent this huge number of states we're talking about for some massive problem. Maybe it's protein folding or chemical analysis or factoring big numbers. So that really started the whole idea of quantum systems. And what the idea was, let's take a quantum phenomenon, something that can be a qubit, and map a problem onto it and see if we can find an answer. So a qubit versus a bit. So I think we all know what a bit is. A bit is a one or a zero. It's what we run all of our digital systems on. A qubit would be a quantum bit, and it again is also a one or a zero. But you create that one or a zero with some sort of quantum state. So we use superconducting Josephson junctions. You can use ions. You can do charge states. But basically, the thing is, because it's a quantum system, it can be in a superposition of that one and zero. So it could have a probability of being a one and a probability of being a zero at the same time. We say that's in a superposition state. So in a sense, you are testing both states. That's not really what you're doing, but that's sort of the good intuitive way to think of it. Moreover, you can take two qubits and you can entangle them so that they both are in some superposition of a one or a zero state, but they're linked in a very eerie way that Einstein called spooky action at a distance, where once you've measured one of them and get an answer, the other one immediately is determined. It's going to go one or zero, depending on how you've interlocked them together in this entangled state. So in that sense, you could think about if you had hundreds or millions of these all entangled, measuring one suddenly sets the state of all the rest of them. So again, this sort of massive parallelization to try and do it. There's a lot more physics behind what's actually happening there, but if you think about it really as being a way of testing huge numbers of states of possible answers to a problem at once, it gives you a feeling for why we think quantum systems could handle certain problems much better than classical systems.
What sorts of problems?
So any problem, the one's probably the most famous is factorization. So people worry, by the way, that quantum computers will break the internet. All encryption will be broken as we know. And it is true that if you had a large enough quantum system, you could factor very large prime numbers. That was one of the first algorithms that actually was proven to be better on a quantum system by Peter Shor back in the 90s. So that would be a problematic thing because a lot of our encryption today is based on not being able to factor very large prime numbers. And the reason it can do that is, again, it can look for all the possibilities, like all the states you're looking for to figure out what are the two factors that go into this giant number out there. Now, I will say that this is a concern, but it's a concern that we already know the answer to. First of all, you need a system that's millions of qubits in size, and we are basically at just over 100 qubits as an industry right now. And these are very noisy qubits we have today, and they aren't even really high enough quality to do anything with. So we've got at least a decade before you're going to be even close to it. But secondly, we already know ways of doing encryption with classical systems that cannot be broken by a quantum system. The math involved with them doesn't map onto a quantum computing system any better than it maps onto a von Neumann system. So you would still be secure. So we are already, as an industry, working with NIST, more of the public-private partnership as well, coming up with standards for quantum safe cryptography so that won't be an issue. So that's the one I think people think the most about. The ones that are probably nearer term, basically doing quantum chemistry. So if you are trying to simulate a chemical reaction or a molecule or how two atoms are going to bind together, that's a quantum problem by its nature because, of course, the atoms themselves and the electrons that do the interaction are all quantum states. Today, even our largest supercomputers, you can only simulate things that are maybe a few atoms in size before you have to make a bunch of approximations, because you just can't go through all the configurations of every electron, what state it could be in, and how it could be superimposed and entangled with that state. You just can't do all that math for anything more than a couple. If you're using a quantum system, you're using qubits, so they themselves can be in entangled states, and they can, in a sense, mimic what's happening in the quantum chemistry world. So that's where we think that even having the kind of noisy qubits we have today, even only having maybe a few hundred of them, you can already start to simulate things you can't simulate any other way. So that's why I think it's really exciting in the near term.
You mentioned superconducting quantum bits. I know IBM uses a superconducting processing architecture. Can you talk a little bit more, and noise? Why does a quantum computer, an IBM's quantum computer, look like it does? Because it's spectacular.
It looks so cool. That's why. No, it really is form following function in this case. I mean, the point of quantum systems is that they can be in this sort of entangled state, right? They could be, the qubits themselves could be in a superposition. They can be entangled with others. These are very fragile states, because in the end, whenever you measure a qubit, it always chooses a state. It doesn't. You never get like a half one or something. You get a 1 or you get a 0. And the minute you measure it, it chooses a state. So we say it becomes classical, it decoheres, and you get an answer out. The problem is, measure is basically any interaction with a qubit, right? So it's not just a person going and measuring it, it's a phonon hitting, a thermal phonon hitting it, or a bit of electrical noise hitting it. Because anytime it's going to interact with anything around it, in a sense, it's got to choose a state. It can't be in this kind of weird middle state, because that's just not the way nature works. It's got to actually choose something. So we spent a lot of time isolating this thing. So the chip itself is down at the bottom of that huge can you see. Of course, that whole can is a dilution refrigerator, so it's kept at low pressure and very low temperature. And actually, as you go down, each of those plates you see in there are colder and colder. So up on top, it's a balmy like 4 Kelvin, and you go down to lower and lower until you get to the bottom, and it's on the order of 15 millikelvin, right? So 15 millikelvin, 15 millionths of a degree above absolute zero. So it's cold, right? And it's amazing to isolate it that much, but that is, we believe, necessary to actually maintain the states. And at the same time, there's a lot of electrical shielding around it. That's why you see all the metal and things around too, because obviously you don't want stray electrical signals. And even the wires that come down in these coax cables, basically you communicate with a quantum system in an analog state. It's a high frequency, 5 gigahertz sort of microwave signals is what you use for playing with the just junction oscillators. So taking that in, you need to have enough energy go into it to make superpositions or flip bits or do entanglement. But you don't want any extra energy, because any energy you put in has to be cooled off, right? You have to make sure you're constantly keeping it 15 millikelvin. So all sorts of noise removers, as well as ways of making sure the amount of energy going to the chip on each of these coax cables is really well controlled. That's really part of the art of what you're seeing in that beautiful structure.
Yeah, I remember seeing it at CES in 2020, right before the world lockdown, and realizing it's a giant refrigerator with this tiny little high-tech chip in this little silver can at the bottom. Can you talk a little bit? I kind of have this strange fascination with Joseph's injunctions. Can you explain what one is and why they're important for quantum computing? I think they're like one of the coolest pieces of hardware in existence, in my opinion.
Yeah, I know. Actually, they really are cool, because they also are one of those things where it really is quantum. So if you don't believe in quantum mechanics, you see a Joseph's injunction, like, well, that's quantum. There's nothing else you do about that. So basically, a Josephson junction is it's you can think of it as being an oscillator. It's a harmonic oscillator. But what that means is it's a superconducting, in the simplest form, a superconducting ring. So it's a material superconducting, so electron current can flow completely without friction, so it'll flow forever. But you actually put in a little bit of insulating material there that they can tunnel through, and you do that because then you basically can control it into flowing. You think about it flowing right or left in the loop. It's one way to look at it. So you have a flux that's going up or down, a magnetic flux going up or down through it. But by putting that little bit of nonlinearity in the system, allows you then to actually controllably take it into either the first harmonic or second harmonic state, or usually go between the ground and the first state, back and forth. So you have an oscillator with a nonlinearity that makes sure that you can actually isolate the two states you want to go between. And then by tweaking it with a little bit of current now and a little bit of a high frequency microwave, you can actually force it to go to one state or the other, or you can try and read out what it's actually doing. So it's a very fascinating little device, and it really is a macroscopic quantum effect in many ways.
And fun fact for our audience, that's actually the reference volt as defined by NIST uses a Josephson junction to get, this is, what 10 volts is, because it's precise, essentially, I'd say to the electron, but that's not necessarily the case for voltage.
Right. No, but that's right. Exactly. Because it's a very stable state. It's a very well understood and a known value.
Now, if I wanted to play with a quantum computer, I think IBM will let me. Is that true?
That's true, believe it or not. In May of 2016, we put out the first quantum computer on the cloud, sorry, and it's accessible to everybody for free. It was only 5 qubits, so not particularly huge, but you literally can go on, and you can go on, get an account, and you go on and you can run a simulator, you can build up a circuit, there's a ton of great tutorials, by the way. If you don't actually know quantum computing, there's great tutorials out there. There's a bunch of Jupyter notebooks that other people put out there, think programs to run back and forth. And you can go run it in a simulator, or you can actually run it on the actual hardware. So there are a number of systems now. We have over 20 on the cloud at this point, and many of them are accessible by the public. Not all. A lot of them are also accessible by our clients themselves. But you can go on and run the actual hardware. It's sitting in a basement in New York, running. And actually, I got to say, the uptime's really good on these systems. Even though they are very fragile, once you get up and running, we've been really successful in maintaining them and keeping them going. It's been interesting to watch. At this point, we get over 2 billion executions a day on these systems. 2 billion quantum circuits run on these a day. Over 300,000 users are using these things at this point. So it's been amazing. We put it out in 2016. We didn't know. We thought maybe you get like 10 people who might be interested in going to play with a quantum computer, but it was amazing. Rapidly, we ended up over 100,000 people who had tried it at that point. Because we've had way more than 300,000 people try it. That's our number of regular users today, right? So it's amazing. We've been all 7 continents have hit it, even Antarctica. There was a scientist down there. She was very bored in the middle of winter in Antarctica, so she taught herself quantum computing, has been using it as well. So it's been interesting to see.
That's fantastic. What is the benefit of having something like that? And the AI tools that IBM has are also open source. What's the benefit of doing something like that and making it generally available?
Yeah, I think this gets back to this whole collaboration that we've talked about. It's so important in research, but it's important even in this area of research, is research heading towards actual product. This belief that getting the crowd working on this stuff is just the better way to do it. I want to believe that we've got all the smartest people in the world working at IBM research, but I know there's other smart people out there too. So let's actually make sure that everyone's going and looking at this stuff, right? In the quantum world in particular, because we are really just learning not only how to build the hardware and make it more stable, but how to do things like error correction, or even like what structures of hardware make sense. And we've talked about the GPUs being good for AI. Well, we don't know what's the right configuration of qubits on a system to run specific algorithms yet. And it might be that there's one version that's really good, or it might be you're going to have different ones for chemistry versus materials versus machine learning, et cetera. So having people play with that stuff and do it, you learn from that community. And in fact, we open sourced our entire software development kit. The KISS kit is completely out there for people to contribute to, because in order to get that to be usable by the community, we want the community to be part of it. We want people who are experts in chemistry writing up libraries to help us understand how to actually do chemistry better on quantum systems. We want people who really are looking at how you control the pulses you send into the individual qubits to help us figure out how to do that better. So we don't, because every time we try and flip a qubit, you run the risk of creating noise. It's going to flip some other qubit you didn't mean to, right? So we're constantly learning this stuff. And the more people we have touching it, the more we believe we're going to make advances that will certainly help us to the work doing, but we think help the whole quantum community as a whole.
Is there anything else out there that I should know about? So there's the AI hardware composer, it's open source. There's the quantum computer. Mm-hmm. What else should I go play with?
So we actually also released something earlier this year, a little more on the software side, called Codenet, which is all about helping AI learn how to write code. So there's all this work right now to figure out how we take code for all of our legacy systems across the industry to move them on the cloud, right? Really make them containerized, to be able to modernize them, et cetera, or even taking like old COBOL and getting up to a more modern language, right? All this stuff. It's extremely difficult, painstaking work. And there's been a lot of attempts in the past to try and write rules-based systems to try and figure out how you translate, say, COBOL into something more modern like Python, right? How do you actually do that translation? The rules-based stuff just doesn't work very well because there's so much context about what that program was really supposed to be doing. So using AI to do that would be a great way to do it. So have an AI system that understands the programming language. It's just another language. If it can understand English and Chinese, it can understand how to actually read a code and translate to a different code. So we released a huge data set of system of AI, of machine learning, as well as regular snippets of code to help AI systems be able to train and learn on it. Because we want, again, we hope you'll contribute to it and use it, because the bigger base we've got there, the better we're going to get AI systems that can help us translate code in the future.
Is this kind of a GitHub Copilot sort of situation?
Yeah, so some of that, exactly right. Actually, another one we just released is something called Cloudflare, which is actually done based on the Ray technology out of Berkeley, but it's actually helping to forget about translating code, but can you just help to distribute the code you've got more efficiently in a Kubernetes-based system to actually get out in the cloud to run more efficiently? Because that's particularly in a hybrid cloud world, which we really believe it's going to be, where you aren't just running on like a single public cloud. You're probably running on multiple public clouds. You're probably running on-prem at the same time. You probably got your own private cloud and data center you're running. How do you move code around and data around and actually get things to run all efficiently? Obviously, we bought Redshift or Red Hat a while back, and so OpenShift we believe is a really good platform for that. But still, how do you get your code properly distributed across there? Cloudflare is actually a technology we think can help that.
So we're pushing up on time. Is there anything that you're geeking out on now that maybe is outside of the conversation today that you're really excited about?
I will say, actually, we touched on briefly the whole idea of genetics right now. The fact that we can actually do stuff there that we haven't been able to do in the past. CRISPR obviously is a very exciting technology there, but getting back to my EE roots, thinking about how do we actually go and think about the hardware necessary to, whether it's solving the algorithms or being able to actually parse through genetic material more incredibly well, or even interface in with biological systems in the future. I think it's a gigantic area out there. It's not necessarily something that I spend time during my day job on, but at the same time, I think it's just a fascinating area that we're going to see develop over the next few years.
If you had to, as a final question, we talked about Moore's Law. If you had to have a Dr. Welsers Law, what would it be and why?
Oh my gosh, what would my law be? Well, I would love it to be something to do with how rapidly you take a technology and see it actually penetrate into an area. So if I think about cell phone technology, when you first got the first smartphone out there, that was really interesting. But how long did it take to actually go forward to actually change everyone's life? And could you actually start to chart what that law would look like? It's not actually something that's necessarily in my field, but at the same time, it's something I think is very interesting. And I think it could help us think about, when you think about a new type of research, how can you think what that impact is going to be long term? Because oftentimes not the direction you thought it was going to be, but if we could understand more about how it does disseminate, I think that'd be really interesting.
Understood. Well, thank you, Dr. Welser. It's been a pleasure having you. Thank you so much for your time.
Thank you. It's really been fun.
Can you imagine being directly involved in that many cutting-edge initiatives? But I guess someone's got to keep the Moore's Law candle lit. Thank you to OKDo for sponsoring this keynote. Find them at okdo.com. You can watch the video versions of these keynotes and catch one of the other 50 live sessions from Industry Tech Days 2021 on the website. If you like this podcast, you are certain to find a session or 20 that will pique your interest. So head over to allaboutcircuits.com and check out those sessions. Thank you for joining me today in the lobby. This podcast wouldn't exist without you. I'm Daniel Bogdanoff, and I'll catch you next time.